Thanks for coming. So today we have a Ting-Wei Chao, right, from Carnegie Mellon University, Asia program. He's a graduate.
Entropy, which is an extremal combinatoric problem, purely so I will start from the instant geometry part. So we all know that in the two-dimensional space, if you have n lines, it determines at most n choose too many two-wise intersections. Right? So the natural question is can we generalize this one, the statement I said, into higher dimensional space? So the natural question would be, if I give you n lines in three-dimensional space, how many three-wise intersections can we have?
Do you mean three lines intersecting in single point, or?
Yes. So I want to find three, how many points that are passed through by three lines from our set of lines. However, this question is still boring. So the answer is still n squared. Of the order of magnitude n squared. And the construction is really simple. You just take a two-dimensional grid and put all the diagonals here. So we have 4 times n many lines determines n squared many three-wise intersections. But I told you I want to generalize the fact into three-dimensional space.
This is R2.
Yeah, this picture is in R2, and I'm taking a slice of R2 in three-dimensional space. So that's the reason this question is still boring. So I will introduce the definition of a joint. Let's erase this example. Let me tell you the definition of a joint. So a joint will be, so if I give you a set of points, a set of lines in three-dimensional space, L, a joint of L is just a point P such that it falls into it lies on three lines in L. And I also want the direction of these three lines as linearly independent directions. So I don't want these three lines to lie in the same two-dimensional plane. I want them to span their direction to span the whole space. So the natural question is to ask, okay, so again, if we are given the size of L, what is the maximum number of joints? And okay, let's again talk about construction first. So this time we can still take grids, but instead of a two-dimensional grid, I want to take a three-dimensional grid. So it has roughly, the number of lines would be 3. Let's say the size of this is n by n by m grid. So we have 3m squared many lines, and we have m cubed many joints. So the order of magnitude should be something like number of j should be of the magnitude of the exponent should be 3 halves. Yeah, and turns out this problem was open for a long time, and the original one who asked this question adapted this problem from harmonic analysis, and it has some application with Kakea problem, in real space, but I will not talk about that today. And it was proved by Guth and Katz using the polynomial method, showing that this is actually the correct order. So theorem. like Guth and Katz. Say that if the number of lines is n, then the number of joints will be less than or equal. Okay. And turns out that the dimension 3 is not really important. We can generalize this to arbitrary dimension. So in higher dimensional space, a joint is just simply in d-dimensional space, a joint is just simply a point that is contained in d lines, and these d lines has linearly independent direction. And moreover, the base field is also not important. We can replace R by any field, even finite characteristic. So it turns out it's easy to generalize their argument to d-dimensional space. So in f to the d, we know that if the number of lines is still n, then the number of joints will be less than or of this order, n to the d over d minus 1. Okay. And so it turns out we understand the order of like how large can J be. So we might want to ask ourselves, can we get a tight bound? Can we see which configuration really optimizes this, like this question here? And turns out there is a construction that is slightly better than this one in terms of their leading constant here. So I will tell you the construction. So the construction is basically given by this. So take h1, h2, to hn to be m hyperplanes in general position. So this will be hyperplanes in general position. That means it doesn't have any unexpected linear relation between these hyperplanes. And we can simply take L to be the set of n choose d minus 1. And I'm writing this to represent all of the d minus 1 wise intersection of these hyperplanes. So if you take any d minus 1 hyperplanes, it will give you a line, right? Because every hyperplane will kill one of the codimension. So if you take d minus 1 hyperplane and look at their intersection, you will get a line. Okay, and I'm going to take my set J to be all the d-wise intersections. And turns out that if I look at any point, any d-wise intersection point, it is contained in a line if and only if the corresponding d minus 1 set of that line is contained in the d set in that point, right? So you can check that this is actually a configuration of m choose d minus 1 many lines and m choose d joints, and if you actually figure out those those constant like d minus 1 factorial and d factorial here, it will be slightly better. Okay, it will be better than this one. So, and turns out this is also the truth. So there's a theorem a few years ago by Yu and Zhao. So Yu is still Hans Yu and Zhao is Yufei Zhao. So they prove that this construction is asymptotically tight. That means if n is really large, then you will not, like the upper bound is not far from this number here by a little of one factor. Okay, and later, so this is the main theorem today. So with Hans Yu, we prove that this construction is actually tight. So we kill this asymptotic this word here. And so let me write down the actual statement. So that means if the number of lines L is x choose d minus 1, and x can be any real number, then the number of joints should be at most x choose d. And we prove the structural theorem for that. Namely, the only equality holds case is that is this construction I told you here. Okay.
If x is not integer, then
Yeah, the bound still holds, but
then the equality doesn't hold, or the other thing?
yeah, so if the equality holds, then x must be an integer, and
okay.
and it must be this construction there.
So the asymptotic type means up to 1 plus this or 1 factor, or just a constant factor.
Yeah, actually they show something like if L is x to the d over d minus 1 over d minus 1 factorial, then J will be something like x to the d over d factorial. Yeah, I think that's
So
equivalent.
1 plus this or 1.
Yeah. So they show something like this, and we are able to kill this factor here. Okay, and I guess people are more interested about more pure graph theoretic problem instead of instant geometry problem. So let me tell you some color about these theorem here. So the first corollary I would like to tell you is the Lowas version of the Guth-Katona theorem. So if you see this formulation here, it might remind you the Lowas version of the Guth-Katona theorem, right? So when d equals 3, it's just simply asking you to bound the number of triangles in terms of the number of edges. And for more general d, the Lowas version, the Guth-Katona theorem says that if you have a family F in M choose B, and you look at the shadow of F, which is defined to be any set of size 1 smaller than any set in F, so it will be in M choose B minus 1, such that B is inside A for some A in your family F. So basically you are taking a family F that consists of some sets of size D, and for each set of size D you drop any possible element there and you collect them. That will be the shadow of F. And it says that the Lowas version of the Guth-Katona theorem says that if the partial of F has size x choose d minus 1, then the size of F should have size at most x choose d. And it is really a corollary because, we can take hyperplane constructions. So we take a set of hyperplane in general position, and this time instead of taking L equals the whole M choose d minus 1 set, instead of taking the joints to be the set of all the dy's intersections, I want to only take a dy's intersection given by this family F. So I'm kind of taking L to be. So I'm actually taking L to be all the dy's intersections. And again, I'm going to take J to be some of the dy's intersection given by the sets in your family F. And by taking these two sets, we can see that every J is a joint of this line set L, and apply our main theorem, you'll get the Lowas version of the Guth-Katona theorem. Okay, and so I keep saying the Lowas version of the Guth-Katona theorem because the original Guth-Katona theorem can do something slightly better than that. So as you mentioned before, if this x is an integer, then we are good. But if this x is not an integer, this bound might be slightly off from the optimal bound. So let me tell you something about the Guth-Katona version of of the Guth, like the original version of the Guth and Katona theorem. So if we take d equals 4, the Guth and Katona theorem predicts that if the boundary of the partial f has size 12, which is 5 choose 3 plus 2 choose 2 plus 1 choose 1, then the size of f should have size at most. You raise all. So I'm expanding 12 in terms of binomial coefficient. I want to do it greedily. Wait. Oh, yeah. Okay, so for d equals 4, I'm expanding that starting from this one to be d minus 1. So this is 3. And I'm taking this number to be the largest possible integer here. So we get 5 choose 3, that will be 10. And then you look at 2, you want to take something that is smaller than 5. So you'll get 2 choose 2 and 1 choose 1 here. And so the size of f should not exceed this sum of binomial coefficient here. So I'm just raising all these 3 becomes 4 and 2 becomes 3. And this number is 5. So that's the Guth and Katona bound gives you. So, however, this is not true in the setting of joints problem. So let me tell you a configuration about on the joints problem that has 12 lines. So I'll give you a construction that the number of lines is 12, but the number of joints is 6. Okay, so let's take rho equals so let's first work in 5-dimensional space. Although here I'm promising you d equals 4, but let's first take a configuration in 5-dimensional space. In R205, let's consider the set of lines to be all the 6 choose 4. So you take 6 hyperplanes and you look at any 4-wise intersection of them, but I'm excluding 1, 2, 3, 4, the set 1, 2, 3, 4, and the set 1, 2, 5, 6, and also the set 3, 4, 5, 6. And I'm going to take my joints to be just any of the 5-wise intersection. And then project everything to 4-dimensional space. So if you look at this construction here, you take any set of size 5, you can see that there will be exactly 4 sets of size 4 inside that set. And the actual configuration you'll get to be something like this. So you could think of like this one as the picture of this configuration here projected to a 2-dimensional space. So every point is passing through by 4 lines, and in 4-dimensional space these will have linearly independent directions. And you can see that there will be 12 lines because you have 6 choose 4 minus 3, and there will be 6 joints. So that means there must be something that is slightly stronger than Guth and Katona theorem lying between that. Between this actual Guth and Katona bound and our joints theorem. And turns out there is a conjecture proposed by Bollobás and Eccles, and okay, I don't really know how to pronounce his name. So Bollobás and Eccles, they ask something about the generalization of the Guth and Katona theorem. And that's called the partial shadow problem. Waste this one. conjecture. And it is also a corollary of our main theorem. Saying that if you start with a family that has size t, and you want to find something that mimics the shadow of f, but it will just be the partial shadow of that. So that means I want to look at a set which I'm still dropping one element from each set of f. So the family has size, each set in the family has size t minus 1. And I want the property that for any a inside our family f, you can always find b1, b2. You can always find d many sets that lies inside this family f, that lies inside this set A. So if you take t equals d, this is exactly the Guth-Katona theorem, like the shadow problem. And so by enlarging t, I'm only looking at part of the shadows. So you have t elements that I can drop, and I only drop d of them and obtain my b1 to bd. So this is the partial shadow problem, and Bollobás and Eccles conjecture that the Lowas version of the Guth-Katona theorem, that bound still holds in this set. And actually this example is also given in their paper. They say that this is actually something that is different from the original Guth-Katona problem. So it has a construction that is larger than the Guth-Katona bound. Okay, and turns out this is also a corollary of our main theorem. So
T is smaller than T.
Which one? T will be larger than T is at least D. So each set A has size T, and I can pick D of them to drop that entry. So drop that element there and obtain my B1 to BD. Yeah.
So B1 up to BD are chosen from G, right? So these are the
they're also in G. Thank you.
And does every element from G needs to be a subset from something F?
So if G is larger, then I'm just enlarging the left-hand side, right? And that doesn't really matter. Okay. And okay, I guess the proof of this color is kind of identical as before, right? You just like something happening here. You just take the set L to be the set of lines defined in t-dimensional space, and J also defined t-dimensional space, and you project that thing to d-dimensional space, and apply our Jones theorem.
So is this the only proof that's known of this?
Yeah, great. Yeah, I agree. I'm glad you mentioned that, and yeah, I also want to bring this question to everyone. Like, is this the only known proof, like, to this corollary here? And so the state of art is that Fitch proved something about d equals 3. He proved that the Guth-Katona bound holds for n being large when m is large. When the size of f is large, then the original Guth-Katona bound holds. And he also proved this conjecture for d equals 3. But for general D, the only known proof is given by you first prove our Jones tight bond and then do this reduction here. Yeah.
So here the setup is the F is a subset of the F is a collection of T subsets of the F,
yes.
right? Is G, what is G? G is
So G will be a collection of T minus 1 subset, and you can think of like I take any set F, and I'm allowed to choose any of the, so there will be T elements in that set A, and I'm allowed to choose D of them. And I drop any one of them, I will get a set B, and I collect all of these results I obtain.
So in the statement, G is a subset of that, right? So
yes, so G is also a family.
yeah. So in the statement, for instance, I can take G to be empty, then it's obviously first. Maybe I missed something.
It's a condition for every set.
Yeah,
of
so I need this condition here.
Oh, you have that condition. Okay, so then what is the statement?
Oh, sorry. I mean, the statement is similar as before. I forgot to write that.
Sorry.
So the size of F is, okay, if the size of G is n, is x choose d minus 1, then the size of F is at least x choose d. Yeah, I'm sorry, I forgot to write an actual statement and make confusion.
Okay.
So, are there any other questions?
But in the Lowas and Katona, if the shadow size of the shadow is fixed, then the size of the original family is upper bounded. But in this statement, the inequality is.
Oh.
No.
I'm sorry. Any other questions? So I guess in the remaining 20 minutes, I want to give you some taste about how polynomial works and how our method are able to obtain the optimal bound. Let me give you some proof idea. And instead of proving the main theorem, I guess it's hiding here. Instead of proving this main theorem, I will prove you a theorem in two-dimensional space, and I will prove you a statement in two-dimensional space, and the statement will be really easy. So let me first write down the statement. I'm going to prove that in R2, if you have n axis parallel lines, that means all the lines are either horizontal or vertical. And I'm also assuming, so in two-dimensional space, a joint is just a two-ways intersection of like an intersecting point. So I'm also assuming that n joints per line. That means I want to assume every line contains exactly n joints. And in this setting, I want to prove the number of joints is at most n choose 2. So this statement looks outrageously easy, but I'm going to use polynomial method to prove that. So let's consider a polynomial f in two-dimensional space. And we also assume that the degree of f is less than d. And moreover, we want to put some constraints on f. So I'm going to ask f to satisfy these constraints. So I take the derivative of f . So I take the derivative of f along the x direction alpha times and along the y direction beta times. And I evaluate that at the point P, where P is inside my set of joints. And alpha plus beta will satisfy all these constraints. So I want alpha and beta to be at least 0. And alpha plus m times beta is less than or equal to d. And m times alpha plus beta is also less than or equal to d. So recall that d is the degree of f we set here, and m will be the number of points per line. So in this whole setting, if I can prove that all these conditions tell me that f must be the zero polynomial, then I can do dimensional counting. So because this is a vector space, because you take any two polynomial and of degree less than d, you add them together, you can get another polynomial, and you can do scaling, so that's a vector space. So we know the dimension of this vector space, And this will be linear conditions on that vector space. Because you can think of that vector space, the variable of that vector space will be just the coefficient of in front of, like for example, the term x squared y. The coefficient here will be just a variable in your vector space. So, and you take derivatives, you just get another polynomial expression, and you plug in this value p. This point p, you will get a linear equation, in like linear in terms of those coefficient of f. Okay, so if I can prove this one, then that means the number of equations I put here is at least as many as the dimension of this space here. So let's first see if I can prove this claim here. So I will postpone this proof later, and let's first see what result we can get. Okay.
So you mean that this is 0 for all possible combination of alpha beta with
Yeah, for all alpha beta
Yeah.
satisfy these, and alpha beta being integers, and for all points inside our set of joints. Okay, so once we prove the claim, we can conclude by dimensional counting that. So the number of conditions is at least as many as the dimension of that space, right? So if this space is V, okay, and it's a high school combinatorial problem to count the dimension of that space. That's the same as counting all the monomials, like x to the alpha y, x to a y, y to the power b, so that a plus b is less than d. So the number of combinations will be just d plus 2 choose 2. And in the left-hand side, since we are putting the same amount of linear equations at each point, so you should expect something like the number of joints. Okay, I'll just write j. So the number of joints times the number of possible alpha and beta. And if you look at these three inequalities, it looks like they look like this. So you are actually counting all the number of integral points in this region here. And and we know that the number of integral points in this region will be asymptotically the same as the volume of this space, right? Or the volume of this shape here, as far as I take d goes to infinity. So we know that this is roughly j times, and okay, so this will be d squared over n plus 1 choose 2 times 2 factorial. And so this part is just the volume of this shape I'm drawing here. And the right hand side is roughly d squared over 2 factorial. Because we're going to take d goes to infinity, so the lower order term here doesn't really matter. Okay, and so we have some inequality involving j and m. So we also want to express m in terms of j and l. But we're assuming there are n points per line. And each point is counted twice, right? Because it is contained in 2 lines. So we know that m is actually 2 times j over l. And if you plug this inside here and rearrange everything, so this d squared is cancelled with this d squared here, and this 2 factorial is cancelled with this one here. So get j is at least n plus 1 choose 2. And if we assume j is a choose 2, so if we say j is a choose 2, then a is at least n plus 1, right? Because this inequality tells you j is at least n plus 1 choose 2. So this is the same as 2j over l plus 1. Again, you plug in j equals a choose 2, and you move this negative 1 to the left hand side and divide everything, you'll get L is less than or equal to 2 times A choose 2 divided by A minus 1, which is exactly A. So because of the help of this volume, like the volume of this one is actually can be expressed in some binomial coefficient, and that really helps us to get a tight bound. But it remains to prove this term here. Okay, so let me try to prove the term in a special case. So let's plug in some value for D and M for the sake of demonstrating the proof. I promise you that the whole proof will be the same. Okay, in this case. So let's say D is 10 and M is 3. So the set of alpha and beta will be like this. So you have 0, 0, 0, 1, so 1, 0, 2, 0, and 3, 0. 1. Okay, so there are 4 inequalities. So the first one says that alpha is at least 0, and the first one says that alpha is at least 0. Second one says that beta is at least 0, and the third one says that. Okay, the third one is this one. I give you alpha plus m beta is less than or equal to d, and this will be the fourth inequality here. Okay. So, and the picture of our joint configuration should be something like this. So you have many axis parallel lines, and you have many intersections, and every line contains three joints. So if you stare at any of these horizontal lines, then you look at the evaluation of f on this line. You look at this polynomial here. Then that is vanished at this point 4 times, because we know f of this point is 0, and the x derivative of this point is also 0, and you take derivative twice, it's still 0, and 3 times. So it vanishes at this point 4 times. If we look at this polynomial here, so this is a one-dimensional polynomial, and so it vanishes 4 times here, 4 times here, 4 times here. But the total degree is 10. That means this must be the 0 polynomial on this line. So this is 0 on this line arrow here. And similarly, if I look at this polynomial, the partial of the y derivative of f, and I'm still restricting to the same line. And in this case, I'm looking at the second law of this expression here. So I take the y derivative once, and it still vanishes at this point 3 times, because I have these 3 conditions. So it vanishes here 3 times, 3 times, and 3 times. And this time, the total degree, instead of 10, the total degree becomes 9. Right? So the degree of this polynomial here is at most 9. So does this polynomial here. And we have 9 conditions, and the degree, so we have a polynomial of degree less than 9 that vanishes 9 times on this line. So this is also the 0 polynomial on that line. So and similarly, this one, and also this one, not this one. So we know these 3 are identically 0 on these horizontal lines. That means all of these numbers, all of these coordinates 4, 0, 4, 0, dot, 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 and so if you look at the partial derivative of these, like alpha and beta being these combinations, and you restrict to any point p, these are you still get a 0, right? Because f is identically 0 on this line, so the fourth derivative along x direction is also 0, and so on. Okay, so we also know this one. 2, 2. So we know all the horizontal, like all the points that has its first coordinate being, has its second coordinate being 0, 1, or 2, are like you have those vanitions, right? That means, okay, let me write down the statements. Beta less than or equal to 2. By this argument here, we know that. So at the beginning, we only know for those alpha and beta satisfy this inequality, it is true. And after this argument, we know that it holds for any alpha with beta less than or equal to 2. And similarly, we can look at the vertical direction. So it's also true for any alpha. And also true for any alpha less than or equal to and any beta. So we also know this part vanishes. And again, we can look at this part by taking the x derivative many times and look at the restriction to this derivative on that line. So we can also conclude that this part should also be 0. That means any derivative of f is 0 at some of the point p. So f must be the 0 polynomial. Okay, so in the next 5 minutes, I'm going to talk about the idea of how to drop these outrageous conditions. So the first one I would like to drop is x is parallel. So so we still put the same set of conditions here, same set of linear equations here. But instead of doing this kind of argument, we want to induct on the multiplicity of f at each point. So because we know that the multiplicity is invariant under change of coordinate, so we don't really need x is parallel here, and we can still do a similar argument to prove that f is still a 0 polynomial by using the fact that multiplicity is unchanged under any change of coordinate. Okay. And the second thing I would like to draw is this m joints per line. So imagine that you have a line that contains many joints. And in this direction, I only need fewer conditions along this direction, right? So this shape here, the length here might be shorter, and the length here might be longer for some lines that contains fewer points. But you still have a condition from here. When you do induction, you will see some condition dropping from there. So you don't have really free choices for picking these lengths. But these lengths must satisfy some equations, so we need to focus on those equations. And we want to try to solve so we want to solve the equation given by, okay, so when we're doing dimension counting here, we want the number of linear conditions we put at each point are to be roughly the same. So we want to solve the equation obtained by shorten or longer this length here, and so that the volume of this shape here is the volume of the shape you obtain in any other joints. So we want to make this volume here to be a constant. And so in this way, you can still get a lower bound in terms of j times something, and everything will still work. All the calculation there will still work. And the last thing I would like to drop is this one. So everything I said works in higher dimensional space. Yeah. So that's roughly the idea of the proof, and I hope this gives you a little bit feeling about how the numerology works and how polynomial method in general works. And I have some open questions. So the first open question is, as the audience have mentioned, so let me erase that. proofs. So the first open question is that can we prove the partial shadow without using the polynomial method? So we don't know yet. And we also try to use some more pure combinatorial way to approach these type of Guth-Katona problem and also the partial shadow problem. And there are also some pure extremal graph theoretic problem coming from the other variants of joints. So if you know what is multi-joint, we can look at a graph theoretic version of that. And we also try something using more combinatorial arguments, such as the entropy method. And we try something and also have some results, but there are still many cases we don't understand yet. Any other questions? I guess that's it for today.
Thank you. Any questions?
For your earlier result about the equality, or maybe slightly. So is there some stability result about that? Maybe J is very similar to X choose D then.
Okay, so stability fails a lot. So if you want to take one more joint, let me try to say that correctly. So one notion of stability is that you might want to prove for any line. So in three-dimensional space, if you take a line and look at all the joints on this line, if you take the hyperplane construction, then the hyperplane defined by the plane defined by this line and this line will be the same as the plane defined by this line and this line. Right? Because if you only look at the hyperplane construction, because it is the intersection of two hyperplanes. So this hyperplane and this hyperplane there must be only two hyperplanes that is on this line here. And this kind of stability fails if we allow one more joint. Because for one more joint, I think the only thing we can, something we can do is just put another line with D minus one other, sorry, put an extra joint with D minus one other lines that pointing in some other directions. So we cannot expect something like this. There are only D hyperplanes uses this line. And also, if you allow some more room, so if you allow constant loss, saying you allow like C more times many joints, then we have a construction that no hyperplane. Okay, this is 3 dimensions, so no planes contain more than 3 or 4 lines, and that is really just a twist of some cube. And yeah, so I hope that answered your question. So stability is really hard in this question.
Any other questions? In the last part of the proof, I mean, you have this lemma on polynomials, right?
Yes.
I missed the part how do you construct some polynomial starting from?
So I'm looking at an arbitrary polynomial in this vector space.
Yeah.
And I'm saying if that polynomial satisfies all these linear equations,
Yes.
then that must be the 0 polynomial.
Right, but
So-
how do you connect to the statement that you want to prove?
You mean the original statement?
Yeah.
Yeah, so if I can prove that is the only trivial, like the trivial solution is the only solution,
Yeah.
then the number of linear equations should be at least the dimension of the space. Right? Imagine you have 3 variables and you have you have 4 equations, and so you have some equations, and that is enough to guarantee that the only solution is the trivial one. Then the number of equations should be at least 3. Right?
Alright. But for instance, I don't see where you use the condition that the lines are axis parallel, for instance.
So for axis parallel, it's used in this proof. So it's used in proving this claim here.
Oh. Okay.
Yeah. So I'm looking at a polynomial that satisfies all these constraints, and I claim that this must be the 0 polynomial. And then, so I can do dimension counting. I can count the number of equations and the dimension of the space. And in order to prove that claim,
Yeah.
I'm assuming they are axis parallel. So if it is not axis parallel, then you take the y direction derivative here at this point here might not be the same as the y direction derivative here.
Okay, I see. So that's where you.
Yeah, that's where I use axis parallel.
Any other questions?
When you're talking about those kind of derivatives, you said some arbitrary field. And
Yes.
In here, you only consider R. So, what is this method is usually the regardless of our field, or you only consider the line configuration of line configuration for the real field, or?
Yeah, and I'm still consider configuration of lines in those fields.
Yeah, but
And
the method only.
yeah, the method also works, but the only difference is like we need to replace this notion of derivative by Hasse derivative. So that's one of the good notion about derivative on finite fields, or like field of finite characteristics.
Hasse, H-A.
Yeah, H-A-S-S-E.
Uh-huh.
Any other questions? So if not, let's thank the speaker.